7, Unit 2, Solving, Lesson 8, Part 2. Inequality Basics, Vocabulary and Notes. On page 33 in your notes, today we're going to be working on verifying a solution to a linear inequality, graphing a solution set to a linear inequality, translating verbal phrases into linear inequalities, and modeling situations with linear inequalities. So first, the vocabulary term, inequality. It's a statement that compares the magnitude of two expressions. An inequality will have one of the 5 inequality signs: less than, greater than, less than or equal to, greater than or equal to, and not equal to. Boundary point is a value where a solution set ends or begins. For example, for x is less than 3, 3 is a boundary point. There are two types of boundaries: open boundaries, a boundary value not included in the solution set. For example, for x is less than 3, 3 is an open boundary because 3 is not a solution. It has to be less than 3. A closed boundary is a boundary value included in the solution set. For example, x is less than or equal to 3. 3 is a closed boundary because 3 is included in the solution. A solution is one value that satisfies the inequality. For example, for x is less than 3, 2 is a solution. 1 is another solution. Any number smaller than 3 would be a solution. And solution set is the set of all possible values that satisfy the inequality. For x is less than 3, the solution set is x, such that x is less than 3. A picture of the solution set is shown here. You can see the open boundary at 3, and it includes all numbers to the left of 3 on the number line. So here's the 5 inequalities and the things you need to know about them. The x is less than, notice it's an open boundary. It does not include your boundary point. So it's an open boundary. Same thing with x is greater than a, open boundary, but the arrow goes larger. Notice the key words here. Generally, if you have less than, fewer than, cannot, those are key words for x is less than. More than, greater than, and the word cannot, which I will talk about that in a moment. The x is less than or equal to a. That is a closed boundary, meaning it includes the boundary. X is greater than or equal to a is also a closed boundary, meaning it includes that boundary point. Keywords here for x is less than or equal is less than or equal, at most, no more than, and possibly can. X is greater than or equal to a, greater than or equal, at least, no less than, maybe even the word can. X is not equal to a. This is not one we will be using much in 7th grade, but it is an inequality sign. It is an open boundary. It is not included, but every point to the left and to the right of the boundary point is included because it's everything except. In fact, not equal to, not, everything but, and cannot. So for the cans and cannots, it depends on the context of the situation. For example, you can have a driver's license when you are 16. Means your age must be 16 or greater. So that would be greater than or equal. Another example, you cannot fit through the door without ducking if you are 7 feet tall. Means you will have to duck if you are more than 7 feet tall. Meaning greater than 7. Now, for these cans and cannots, you have to use your life experience to figure out whether it's greater than or less than, and whether it includes the boundary point. Let's look at some examples about verifying a solution. You can verify a solution to an inequality using substitution. Substitute the value of the solution and simplify the inequality statement until the truth value of the inequality can be determined. If the resulting statement is true, then the solution is verified. Consider the two examples below. Determine if x equals 13 is a solution for 2x plus 19 is less than or equal to 31. First, we substitute in x equals 13. We'll have 2 times 13 plus 19 is less than or equal to 31. Well, 2 times 13 is 26, and 26 plus 19 is 45. 45 is not less than 31, so x equals 13 is not a solution. Second example, determine if h equals negative 4 is a solution for 3/4 h plus 7 is greater than h. 3/4 times negative 4 plus 7 is greater than negative 4. We're going to substitute in h equals negative 4. Then we simplify. We end up with 4 is greater than negative 4, which is true. Therefore, h equals 4 is a solution. Tell whether negative 2 is a solution for each inequality. We're going to plug in negative 2 for the variable and just see if this is true. So negative 2 minus 5 would be negative 7. Is negative 7 greater than negative 6? Well, that is false. So this is not a solution. Next example. Negative 5.5y less than 14. We're going to try in negative 2. So negative 5.5 times negative 2 is less than 14. Negative 5.5 times negative 2. Negative times negative is positive. And 5.5 times 2 is 11. Is 11 less than 14? That is true. So yes, this is a solution. Write an inequality for each statement, then graph the inequality. Remember to number the graph. The statement: you have more than $3 in your wallet. Let's make M equal the money in your wallet. Now, if M is the money in your wallet, M is my variable. It compares to the number 3. If I have more than $3, well, I can't have exactly 3, but I could have anything greater than 3. So M is greater than 3. Now, the most important number on this number line is going to be the number 3. I'm going to put some additional numbers on there, though. Make sure that they're in order. They go from being less to the left and more to the right. The boundary point of 3 is not included. And M is bigger. Since M is greater, my arrow shows all numbers greater. It goes towards the bigger numbers. Example 253. Yvonne has no more than $10 to spend on snacks at the carnival. Let's use an S for snack money. So the boundary point is 10. My variable that I'm using for snack money is S, and she has no more than $10. So she could actually spend $10, so that is going to be or equal to. But can she spend more or less? If she has no more than 10, she can spend less than $10, but no more than. So S is less than or equal to 10. The most important number on this number line is going to be the number 10. So I'm going to make sure it's on there, and then do a little bit more labeling. You don't have to necessarily label every tick mark. You just have to be in order from least to greatest when you go left to right, and they have to be equally spaced markings. So we include the boundary point of 10, and we're going to include everything smaller than 10. Now, one thing about this problem to consider: it is not possible to spend negative amounts of money. So this actually technically only goes down to 0, because Yvonne's not going to be able to spend a negative amount of money. Okay, Heather goes to a restaurant for dinner and is told there is more than a 25-minute wait. Let's use W for the wait time. And now we're comparing W to 25 minutes. Now we're told there is more than a 25-minute wait. More is just greater than. Could it be exactly a 25-minute wait, depending on the wording here? It says more than 25 minutes, so it's going to have to be greater. Most important number here is going to be 25. And I'm just going to go ahead and count by ones, but skip count every other thing, every other dot. tick mark by 2. So 25 is not included, but W is greater than 25. We're going to draw an arrow indicating all numbers greater than 25. Okay, Patrick lifts weights. He can lift 120 pounds on the bench press. So let's use L for the lifted weight. Okay, we're going to compare L to 120. Now this doesn't have any key words in it except the word can. You're going to have to use your life experience. If Patrick can lift 120 pounds, that means it's going to include 120. Now does it mean Patrick can lift 120 or more? Or does it mean Patrick can lift 120 or less? Well, based on my experience, if you can lift 120, you can also lift 80. You can also lift 40. You can lift anything less than 120. So on my number line, I'm going to include the number 120. I'm going to go ahead and count by tens, but label every other tick mark, so I don't have to write quite as much. Now 120 is included. He can bench 120. He can bench anything less than 120. So the arrow would go towards the smaller numbers. Because L is smaller, the arrow goes towards smaller numbers. Determine whether each stated value is a solution to the inequality. 5t plus 11 is less than or equal to 27, with t equal to -4. Well, we're going to plug in -4 for t, and we get 5 times -4 is -20, plus 11, that's -9, less than or equal to 27. Now that is true, so this is a solution. Yes, t equals -4 is a solution. Let's move to the next example, example 257. 4/5 of j plus 5 times parentheses j minus 1 less than 24. Plug in a 5, so 4/5 of 5 plus 5 times 5 minus 1 has to be less than 24. 4/5 of 5 is 4. 5 minus 1 is 4. So 4 plus 5 times 4, that's 4 plus 20, that's 24. Is 24 less than 24? No, it actually is equal to it, and since this is not an or equal to, that is false, so that is not a solution. In fact, that is the boundary point, but the boundary point's not included this time. Okay, next example. 2r minus -10, I'm going to change that to plus +10. And then we're going to plug in 6. So 2 times 6 plus 10 is greater than 15. 2 times 6 is 12. 12 plus 10 is 22. Is 22 greater than or equal to 15? Well, that is true. So yes, this is a solution. Next example. 3.4y minus 13 is less than or equal to 4.2y. Alright, so we're going to plug in -3.3 here. So 3.4 multiplied by -3.3 minus 13 is less than or equal to 4.2 times -3.3. Okay, so let's do some calculations here. 3.4 times -3.3. 3.4 times -3.3. I get -11.22 minus 13. Let's go ahead and subtract 13 and see what we get. This is -24.22. And then 4.2 times -3.3 is -13.86. Now here we do have a true statement. -24.22 is less than -13.86. So yes, this is a solution. Okay, next example. We're going to be working on the assignment. Let's take a look here. On number 1, you're going to write an inequality for each statement or situation, then graph the inequality. Let's take a look right here at D. Mike has at least $13 in his pocket. Let's make M equal money in pocket. And the money in the pocket compared to $13. Well, it's at least 13, so it could be bigger than 13, or it could be equal to it. So my boundary value here is going to be 13. It's included. And every number larger than 13 would also be included. Tell whether the given value is a solution to the inequality. So let's do one of these real quick as well. Let's just take a look at D. We're going to plug in A as negative 18. Negative 18 divided by 6 greater than negative 4. Negative 18 divided by negative 6 is negative 3. Is negative 3 greater than negative 4? Yes, it is. So the solution does work. It is a solution. Number 4, you're going to solve and check the solution. Number 5, you're going to evaluate using the standard algorithms. Remember, that means to stack and multiply, moving over as necessary, etc. I'll let you guys finish that. Number 7, you're going to determine the area of a rectangle. Number 6 is a speed problem. You're going 60 miles an hour. How far can you go in 4 hours? Number 7, we're dealing with a package. You're going to write an expression to represent what you can mail, and then on part B, you're going to give 3 examples of packages that are mailable. And then number 8 is a matching problem with compound inequalities. What this statement means is every number between negative 5 and 0, but not including the endpoints. So if we look over here, every number between 5 and 0, but not including 0 and not including 5, this matches up with that graph.